There's a few news stories. This is a very fun talk. What this guy did was he decided to think about obfuscating Bash. Obfuscated PowerShell has been used for attacks for a while, but he wanted to find out how to make Bash hard to recognize, and he found a lot of cool techniques. Like here, you can use this, which you use to inject arbitrary unprintable code. You can use it to put in printable letters. So this is CIT, this is cat. And there's just a lot of tricks like that you can use. You can do this. This with an X, this is hexadecimal. Without an X, it is octal. And on it goes. Very strange stuff. And there are many, many tricks like that. You can use Unicode strings and mix them in with other strings. You can put these ticks in places. If you put the back ticks around some characters, it will just evaluate those characters, leading to the same thing as if they weren't there. And so the ticks will just be obfuscation that won't change anything. You can put in double quotes. You can run strings together in a line of Bash and it will concatenate them. So this is, you can backslash characters that don't need to be backslashed. So this is a escaped G, which is equal to a G, combined with an R to make a two-letter string, then an empty string, then an E, and another string called P, and they're added together to make grep, and it will run. And anyway, the amazing thing is when you do all this, you can make an engine that will do all these things in series. And so he made this tool called Bashful Skater, and what it does is it will turn one line of simple command, the same one, grep something, it turns this one into 11,000 characters of crap. And Bash still executes it, and some of them make 200,000 characters of crap, and it still runs. So it is utterly impossible to understand or read any of this obfuscated stuff, and this is a lot of fun to see. Anyway, this one surprised me. So people, SpaceX engineers are going on the dark web behind Tor and selling inside secrets for traders. Now, they say he went there and sold fake inside secrets, which people then used, which would not really make them money, but I don't see any reason to believe that part or to imagine that he's the only one doing it. And I wonder how much of this is going on. This would totally work. It's clearly some kind of securities fraud, and there'll be a prison sentence, I would think, for it, but I would imagine quite a bit of it goes on, just like any other form of espionage. And this I thought was fantastic. These guys have got windmills that do not have blades. They just wobble. The wind makes it wobble, and it generates energy from that. And so this thing is, I think, cheaper, safer, simpler, and you can stick it on top of a lamppost to power the lamp, and so on. He said it could be a real good way to bring wind power conveniently to people. Bash history will store the obfuscation. Well, it's a good question, and I don't know the answer. My only concern is, he said if you run the Bash debugger, some of these will break the debugger. And I assume Bash history probably has a line length. So I don't really know. I would think, for one thing, you would probably exceed the limit of a line of Bash history, but I don't really know that. You'd have to try it and see. It's a good question. So I hope everybody knows about this. Every time anybody tweets anything about any cryptocurrency, immediately a bunch of scammers will say, send me money and I'll send you twice as much back. And so somebody followed Tesla. Tesla tweeted about Dogecoin. Somebody with an account that looked like Tesla's immediately replied and offered the typical scam that you can reply, send me some Bitcoin and I'll send you twice as much. And this guy sent him 10 Bitcoins, believing it. This happens a lot. And of course, they just keep it and it's gone. And that's the whole thing about Bitcoin. It is intended to reproduce gold. So if somebody steals your Bitcoin, they're just gone, gone, gone. There is nobody to sue. There is no legal jurisdiction. There is no way to get a refund. You're pretty much just hosed unless, for example, you are able to prove who took it and they're also in the United States. Then you might try to prove some of this in court. But the whole nature of Bitcoin is that you will have a very hard time proving who actually got the money. It'll just be some meaningless account number. And so this one I thought is amazing. You can take a smartphone and turn on the microphone and record the sound of sliding your key into the lock. And from that sound, they can reproduce the key and build a working key. So it sounds pretty cool. It would be fun to see that in practice. And this one I mentioned at the last class, which is amazing. It's a great podcast of Bill Nye. The human race is becoming infertile to an incredible extent. 60% decline in sperm count over the last 50 years, caused by chemical pollution that are in all of our bodies. So this sounds really serious, and we really need to do something about it. And that leads to a lot of other side effects. Heart problems and brain problems and lots of things, as there's a consequence for developing humans in the womb if they get exposed to these chemicals, which are all around us in all the products we use now. They're the chemical that makes plastic soft, so it's in anything that comes in a soft bottle, and it's often added directly to things. It makes skin creams soak into your skin better, so it's directly added to the cream. So we really need to use safer chemicals and test them first. Europe apparently only lets you use chemicals after they've been tested for safety in products intended for human consumption, and apparently America does not, which is news to me. So they say there are 1,000 chemicals in use in America in the products you use that you cannot use in Europe. But that is apparently a new law even in Europe, so they do not have any data on how much it actually lowers these health effects in Europe. But it would seem like a really good idea. So anyway, they asked the researcher what an average person can do about this, and she said, don't microwave your food in plastic. That's probably the worst thing you can do. So I think all the people that want to get organic food and only store it in like glass containers and masonry and not plastic containers are all on the right track. And so I mentioned this a few times. I'll just mention it now in case anybody's interested in NFTs. NFTs are these digital trading cards that prove supposedly that you own something, but apparently the current implementation of NFTs, including the one that just sold for $69 million, is terrible because they did not store actual identifying information on the blockchain. The whole point of it is it'll store some proof that you own it on the blockchain, which can never be erased because there are many copies of the blockchain all over the world, and nobody can get to all of them to erase them. That was the idea. But what they actually store on the blockchain is just a URL to a website, which will then have the key. And so if this website changes, or if it gets hacked, or this company goes out of business, the object on the blockchain will no longer prove that you own that object. So what you primarily paid for, you did not get. So that is pretty awful. And so Uber in the UK is going to give drivers a minimum wage, holiday pay, and pensions, and they say the rider's price will not go up. So this seems to me like really important information, so I think the people in the United States can demand the same thing on the same logic. Uber's been trying to say in the United States that they couldn't possibly give their drivers that kind of help or something terrible would happen, but I think there's now precedent to say that is not true. Anyway, here we are at 125. And so this is the second part of Chapter 4. Chapter 4 is really long, so I think I'll just do some of it next time. I was planning to have a guest speaker then, but I don't have guest speakers on Thursdays. What's happened is now we have a regular series of guest speakers on Mondays and Tuesdays, which I highly recommend. And in that spirit, coming up is another episode of the Wireshark CTF. So if you didn't do it last time, you might want to do it this time, coming up on Saturday. And then there's these guest speakers, which are probably the most directly relevant to this class. I guess I don't have the next ones up here yet. Let me see if they're on the website that posts them, because this Bay ICT is the site. I think they do have some, and I just haven't added them to my webpage yet. Yeah, April 5, there's a competition. Tech Talk there. Jimmy Sanders, this looks like one of them. Information security at Netflix. Well, I had another guy from Information Security at Netflix talk, and he was wonderful. So there's one on April 20 anyway. And I would expect there to be another one earlier in April. Maybe it's not up yet. Anyway, I'll put these on my website. I highly recommend these, and also for this class, the FireEye monthly threat briefings. I listened to the first one of these and it was excellent. So I highly recommend listening to these. And you can listen to the one from just a few days ago if you go to this site. They're archived. They're 1 hour long and they are very informative about what kind of attacks are out there and what people are doing about it. So FireEye is the best incident response company in the world. And they release a lot of interesting information about what nation states are attacking us and what kind of criminals are attacking us. And the thing they talked about on this one is how many people are getting hit by ransomware, and how if you hire an experienced company like FireEye, they know the attackers and they know their history, so they can tell you whether you should pay them or not. Because some of them are reputable as criminals go, and when you pay them, they will actually not leak your data and give you the key so you can get your data back. And other people, you pay them and they don't give you your data back. So they can tell you which group has hacked you and whether to pay them or not, which is one of the values of threat intelligence. Anyway, so let's do some of this. Is that the company more advanced than the NSA? Oh, well, I would never say that. Now, nobody knows how advanced the NSA is, really. Everything is top secret. I don't think they're more advanced than the NSA. I don't think anybody is. Based on public key cryptography, the general wisdom I've heard is that the NSA is 20 years ahead of everybody unclassified. So, no, I don't think they're more advanced than the NSA, but I think they have threat intelligence. Yeah, but I never thought of comparing a private firm to the NSA. I mean, the NSA is the military. They're really not the same thing. Yeah. Oh, sure. They probably find things. See, the NSA is not allowed to investigate inside America. This is what they were saying about the Capitol attack or something else. Oh, some of these attacks, these exact attacks, SolarWinds attacks, and the other big one, the Exchange attack. The problem is the NSA is not allowed to look in the United States. They're only allowed to look at foreign adversaries. So that means that our attackers know that. It would have to be the FBI locally. That's why our political separation between the spy agencies limits our response, but private companies don't have that problem. Yeah, I think everybody got hit by SolarWinds. Yeah, and FireEye got hit first, and they're the ones that detected it and told everybody. Everybody else had been owned for like 6 months, and FireEye's the one that noticed and told them. Yes. So this is the same as when Google got hit by China in 2010. All the other companies had already been owned, and they didn't know it. Google got hit, and Google exposed it, and then told everybody like Microsoft and Adobe that the Chinese had hacked them too. So the fact that they got hit, you might think that means they're not competent, but the fact that they were the first to detect it is very good. And unfortunately, there is nobody that's safe. You would like to think a good security company would just not get hacked, but it's totally not that way. Everybody gets hacked. The military, Google, everybody you can think of gets hacked because defense is so much harder than attack. So the only thing you can do, you know you're going to get hacked. You have to have detection and response when you get hacked. You just have to accept it. It's just going to happen. It's like employees theft or fires in the building. These are just things you cannot get to zero. They're going to happen sometimes. So you have to plan of how you're going to respond when these bad things happen. That's all you can do. Anyway, these are very good questions, very good comments. All right, so let's take a look at this Net Plus stuff. This is essentially the whole Net Plus in one chapter. So I'm just as happy to give it another lecture to go through it because it can get kind of dense. If you have Net Plus or Cisco, then you've already seen this. If not, then it's really quite a lot of terms to learn, although you don't have to know them in a lot of depth, but you need to recognize all these terms. So ICMP is the protocol used to send control messages over the internet, most commonly just a request and a reply to show that the network is reaching that other remote server. There are other ones like telling you when a packet was discarded and such. Traceroute sends a series of these packets with different time to live. So the TTL1 expires at the first router and replies, time exceeded. The TTL2 goes here, the TTL3 goes here. So you can trace out which routers you pass through. This is useful if you have a complex network to try to find out what part of the network is giving you trouble. And all right, Unix and Cisco send UDP packets with and Microsoft sends ICMP packets. You can send any kind of packet carried by IP in principle, but those are the packets that these utilities choose to use. So Telnet is used to send command lines. It was designed in the ancient days to just send it down a twisted wire from one terminal to a computer in the same room and then ported to the internet. So now it sends commands and passwords and everything over the internet without any encryption, which is awful and terribly dangerous and should never be used. What you should use is SSH instead, which encrypts it all so that you can send command line commands to a server without exposing them to everybody that can see your traffic. FTP, similarly, was designed in the early days to just send the data and password unencrypted over a network, and again ported to the internet, and again it's very problematic and should have gone extinct 20 years ago. Names and passwords are exposed without encryption, and it handles the ports in a goofy way, which makes it difficult for firewalls to let it through. So TFTP is used to load firmware on IP phones, and it sends files with no authentication at all and no encryption. It's not really appropriate to use over the internet. You should only be using it on a local network, but there were some worms in 2000. Bugbear moved by TFTP. It exists, but it's unwise to use over the internet because, again, it's one of the old protocols that had no encryption. So SSH is the secure replacement. And all the others, you have SFTP for FTP and SCP to copy files, and all these make a secure encrypted tunnel over port 22. The early version had some vulnerabilities in it. The modern version is SSH v2, and it's considered very secure. It is subject to man-in-the-middle attacks, though, because there is no trusted third party. So if you connect to someone and they catch you in the early stages of connection, they could put up a fake server and you wouldn't know that. SNMP is used to send email on port 25 unencrypted, and POP and IMAP are also used to move to local clients, again unencrypted, and there are later encrypted versions on other ports. Encrypted email is very problematic. There was a lot of scandal a few years ago when Hillary Clinton was using unencrypted email, but to reach a lot of people, there's no other choice. Encrypted email is a strange beast, and you really don't have an easy way to know that it was encrypted all the way to the end. It tends to be encrypted on hop to hop between servers. There's not a good system working very well for it yet. DNS is used to get IP address. If you used an SSH public key, would it prevent man-in-the-middle? No. The way that SSH, the problem is you need to know the identity of the server. So what they do is they public print something. Your server has this hash value. They present you like a hash value. And if somebody told you what the right hash value was for that server, you would know it was okay. But usually you don't have that information. That would make it, the only thing that would prevent man-in-the-middle is if you had some other trusted channel whereby you were given the correct hash value to look for. To try to prevent that, what SSH does is the first time you connect, it'll ask you if it's okay, and then it will remember it. And then if you try to go to the same server later and the hash value changes, it will warn you. So the way to use it without being subject to a man-in-the-middle is connect the first time when you're sure it's okay, if you can arrange that somehow. But yeah, I mean, that's why what's better is to use HTTPS, TLS, which has the certificate authorities. That's really secure against man-in-the-middle. SSH is not as secure. Anyway, so DNS uses UDP53 and now sometimes TCP53 for larger data, and it has zone transfers that are used to copy all the data from a server to another server. And if you leave zone transfers available to the world, which is the default maybe 10 years ago, then anybody can download all that data. Now, anything on a DNS record really ought to be public anyway, but unfortunately, a lot of people mix public and private data on the same DNS server, and if they do that, then it can get exposed by zone transfer. The new version is DNSSEC. It's a new added security feature to DNS, which is quite cumbersome, but it's slowly expanding out there. And then server records come with signatures, so you can cryptographically verify that they haven't been altered. So the start of authority tells you where the master record is. Yeah, DOE. DOE is another popular encrypted form these days where you move DNS over HTTPS, and that improves privacy on your local area network. Anyway, a DNSSEC solves a different problem. The only problem it solves is it stops the cache poisoning attack on the server that Dan Kaminsky discovered. And there are other mitigations on that. So DNSSEC is kind of like IP version 6. It's a lot of work to implement, and then you don't actually gain much business benefit from it. DOE, however, gives a strong privacy enhancement to the end user. And it also makes it very difficult for people to monitor the DNS traffic to discover abuse. So a lot of defenders really don't like DOE. But DOE is growing out quickly, and I think Firefox now uses DOE by default. So all your DNS records are encrypted and can no longer be just viewed by anybody around you. Anyway, the most common DNS request is a recursive request. I ask, say, my local router, where is yahoo.com, and it just asks somebody else and finds it and then tells me. That's a recursive record. You could make a non-recursive request, and then you'd ask one server, and if that server doesn't know, it will just tell you, I don't know. There are also caching servers that store resolutions so that you can just have a faster response locally because many people go to the same site and you don't need to keep looking it up over and over. So there's a lot of weaknesses in DNS. It's a very old protocol using UDP with no authentication, no encryption. Preventing a cache poisoning attack on the server depends on a 16-bit source code and a 16-bit DNS query ID. That was the upgrade implemented in 2008 to fix the DNS cache poisoning attack that Dan Kaminsky is famous for. It didn't used to randomize the source port, but now it randomizes both of these, and it is therefore relatively secure against cache poisoning attacks because it's too hard to guess all 32 bits of this random stuff. But DNSSEC cryptographically secures it so that you don't even have that minimal chance of getting in. And adds authentication and integrity to the DNS responses. This does not protect your privacy. What it does is mean that when a server asks another server a question, it can verify that it got the answer from the trusted other server, not from the man in the middle, and that it hasn't been altered. And someday your clients will be able to enforce it too, but only when it's basically universal all over the internet. If you were to enforce DNSSEC signatures on the client these days, most of the internet would just vanish because most servers are not yet employing it. And so you can see it if you use an online dig, like the Men and Mice dig portal. There's a bunch of these called DNS looking glasses, and then look at a website that is using DNSSEC like the Internet Engineering Task Force. When you do a request, it will come with this big signature record. This is the resource record signature, and this long cryptographic mess is the signature that proves that that's really a valid record. So the responses get much bigger, and that's why you often have to transmit them over TCP instead of UDP. And that's why I use these looking glasses, because a lot of local area networks will not let these large traffic packets through. For some stupid reason, UDP-based DNS is limited to 512-byte responses. That's not a limitation of the UDP protocol, it's a limitation of the DNS protocol, but the TCP version can be longer. Anyway. All right, SNMP is used to control network devices like firewalls, routers, switches, and servers by sending command packets. The early version of it sent unencrypted community strings, which are passwords over the network, and usually everyone just left them at the default value of public and private, so anybody could just mess with your firewall. You know, the whole internet suffers from the fact that until around the 90s, everybody's used completely unencrypted crap everywhere, and it was just all wide open, and they just depended on nobody understanding it. But as hackers began to understand it and start hacking everything, they had to improve everything. So now we have SNMP version 3, which adds encryption and is therefore much better. But the problem is, of course, if you have legacy devices on your network that can't speak SNMP v3, many people continue to use SNMP v2 because they don't want to bother upgrading all their stuff, which is a reason why a whole lot of these old things are still in use, because people don't want to replace the old equipment. HTTP is the same, lets you serve web pages with no encryption. This was the standard for a long time. Now, in the last several years, everybody's moving to HTTPS because they found out that this is unsafe for every purpose. The original idea was it was okay to use HTTP to just look at a web page unless you're sending a secret like a password or a credit card number. But the problem is, since there's no encryption, anybody in the middle can alter the page by adding scripts to it or malware to it. So it's not even safe to view static pages over HTTP, and modern browsers will in fact warn you that you really shouldn't be using any page that's just HTTP. Everything should just be HTTPS, so that you have high security to believe that that page has not been modified in transit. Boot P would enable a machine to boot from the network, getting an IP address and then loading the OS over the network, the sort of thing you might want to do when ghosting machines. It's not very common. So would the attacker modify your code and save to your server? Usually what the attacker does is just modify it on the way to the client and then run code. There's a hacking tool in Kali that does this called BEEF, B-E-E-F, Browser Exploitation Framework. You just add extra code to the server and then use a client. So every page you load has extra JavaScript that the developer did not put there. You never put it on the server. It goes on the client. It runs in your browser, and then it calls back, and I can send more commands so I can use your browser to execute commands without you knowing it. That's what BEEF does. And it's therefore not terribly powerful because your browser doesn't have the ability to do a lot of harm to your machine unless you have a vulnerability. But I can do some things. So as you patch browser security holes, this particular attack becomes less powerful. But still, it's a bad idea. I could pop up messages on the screen to make you do foolish things. I could just change the page in any way. It's kind of like the same thing. You ask, what could I do if I hacked your router? Well, if you were using HTTPS, I couldn't do much even if I hacked your router. But if you're using HTTP, I could totally change everything by hacking your router. All right, DHCP is what we all use these days to get an IP address when you first boot up your machine. It sends out broadcasts and it gets all the information it needs to connect to the network, which is an IP address, a default gateway, and a DNS server, and possibly some other information. So this is what's used to assign IP addresses to new clients that join a network. All right, you don't use it on servers because you want servers to just stay at a fixed address because they're tied to domain names. You want people to find them. But for clients and laptops, you typically use DHCP, and so they have a different IP address every time they boot up. Or they could have a different address. In practice, it's often the same, but in principle, you could get a different address every time. So we want 4D here, and there's 4D. Good. And the delay is about 5 seconds, which is good. All right. I'll give it a few more seconds. All right, I guess that's it. Wouldn't VPN cover for HTTP? It would help. It would protect you at least as far as the VPN server. Yes, a VPN adds another layer of encryption to the traffic and therefore helps make up for a lot of these flaws. Absolutely. All right. All right, so what utility sends packets with different TTL values? Okay, that's traceroute. Good. All right, which one sends file transfers with no password? Okay, that's TFTP, no password at all. It just asks for a file, and if that file is there, it just loads it. What protocol runs on port 22? Okay, that's SSH. All right, and what protocol uses RRSIG? Oops, pardon me. Yeah, it's it. DNSSEC has these resource record signatures, which are those cryptographic things, so it can detect alterations in the records. Okay, Joseph. Hello left, tell me who they are if they want their points. And I know who that is. All right. Okay, good. I see hello. Giving me a name that looks a lot more likely to be tied to a student. Good. So, all right. Let's go back to the slides, which are here. Okay. Oh, I see. It's a little bit too broad, but it doesn't really matter. All right. So, all right, network architecture and design. In layer 1, you have these cabling issues. That's where, and so electromagnetic interference is radio waves that affect the cable that's leaking from one wire to another. Attenuation is another problem. The signal at one end of a wire is decreased by resistance, causing some of it to dissipate in the wire and get weaker at the other end. The most common cable is unshielded twisted pair, Ethernet. This is the cheapest, most flexible, and most common wire. It has a different number of turns per inch for these wires to try to make the crosstalk cancel out, but it doesn't have any shielding on the outside, so if you run it near fluorescent lights, it will be affected by them. This is all the issue of electromagnetic immunity. The crosstalk is electromagnetic immunity between these two, and the shield on the outside, which is not here, would protect you from electricity coming in from the outside. And both of those are problems. So you have different categories of cable, which is determined really how many turns per inch is a lot of it. And these days, most everything is Cat 5e or 6. Any cable can run a fast signal through a short run, but the modern, if you get the right cable, you can actually run it the full length, like 100 yards, and still have the full speed. Ferrites too, yeah, you can put ferrite beads on the end to stop certain high-frequency signals from going through the sheath, yeah. I see those mostly on DSL lines where you're trying to prevent the computer traffic from interfering with the phone traffic. Not usually on computer cables. Anyway, so shielded twisted pair is where you put a layer of tinfoil outside that cable, which makes it stiffer but protects it from electromagnetic interference on the outside. And so it'll look like, this is coaxial cabling, where you don't have 8 wires twisted in pairs here. You have one conductor down the middle, and then a braided sheath outside it, so it makes a cylinder, and this creates a waveguide which will take a certain frequency range and send it very smoothly through the cable, as long as you don't bend it through too tight of an angle. So this can carry really a lot of bandwidth and is quite resistant to electromagnetic interference. The braid here nicely stops most of that from getting through, and that's what you have cable TV signals going through. Fiber optic is the highest bandwidth type of cable. It is essentially a perfect transmission medium. Much faster. You can send a signal 50 miles without a repeater through single mode fiber optics. The only problem is that the transmitter and receiver are more expensive, and the connections between cables is trickier. I used to teach this. You have to polish the ends and you have to be very precise and keep everything very clean. because the two pieces of glass have to line up and get so close to touching that they're within one wavelength of light. So, it's much, attaching the connectors, using the connectors is more expensive and difficult than things like coaxial or Ethernet connectors. So typically what people do is they use fiber laid by professionals to the neighborhood, and then you use electric wire like Ethernet to get into your house and between your rooms and such. Fiber all the way to the desktop is usually not worth it. Usually just getting fiber into the building or to the campus is enough, and then using the cheaper Ethernet to propagate it there. How's that propagation distance compared to lower frequency radio communications? Well, I'm not sure how far. I know if you use Wi-Fi, it only goes, theoretically 100 yards, in fact, much less. If you use microwave with real dishes that direct it like the military does, then you can send it line of sight, maybe 50 miles. But that stuff is too expensive for most people. So it depends on how you set it up. I know can't low frequency bend around the Earth? Yes, some frequencies can bend around the Earth. I'm not aware of network traffic being sent that way, though. The problem is you can't rely on it. It depends on the Van Allen belts, and they come and go, and they depend on the weather and the solar storms and stuff. So ham radio operators use it, but I don't think you'd want to rely on it. What people use is satellites. Those you can rely on. Then you can reach a large distance through radio. And that's what Elon Musk is doing, putting up tons of satellites to sell that internet service to everybody. Anyway, so that's fiber optics. And so there's multimode fiber. Yes, Starlink is the thing Elon Musk is setting up. He's going to put up something like 10,000 satellites, and he's got the first few hundred of them up there now. So multimode fiber is thick glass, about 50 microns, and this is lower bandwidth and shorter distance, but the NICs are cheaper at both ends. Single mode fiber is for long haul, high speed. It's more expensive to build the NICs, but you can move a lot of traffic through them. Theoretically, you can move 100 terabits of traffic through one strand of single mode fiber. And wavelength division multiplexing sends multiple signals over different colors of infrared light, and you could easily exceed 10 gigabits per second or even much more. And this is what's really used to move everything long haul on the internet and on the phone network. There are undersea cables connecting to continents, and their wavelength division multiplexing through single mode is what's happening under the ocean to move large amounts of data a long distance. All right. So on your local area network within the building or neighboring buildings, you have Ethernet. Originally used a bus. The early versions would have this thick thing that looks like a garden hose going through the ceiling, and you have these vampire taps connecting each machine. The underwater links are questionable in their security. They tend to get bitten by sharks, so they have to put armor plating on them. Spy agencies go down there and stick taps on them to snoop on them. There are ways to attack them. Yep, there's the shark bite. Yep. The cable's about a foot across with armor plating, and they do also get broken. Right around one of the big, about 15 years ago, before I think one of the Gulf Wars, a whole bunch of them were all broken all at once. And people said, oh, that was just the weather, but a lot of people thought it was like sabotage. So, I mean, certainly you've got, 10,000 miles of undersea cable, you can't really protect it. Anybody could go by and cut it. And they could, in principle, even tap into it and get a copy of the signal and you wouldn't know. So, I don't know if that's really happened under the water. I think it's cheaper to do it elsewhere. But yeah, there's just plain availability is a problem. They do have to repair them and replace them and upgrade them and such. Anyway, so now you use a physical star topology. You have a central device like a switch, and every computer has one cable going that they have complete, that's baseband. One whole wire per device, and that wire can use all the bandwidth in that device. If two nodes transmit simultaneously in an old-fashioned network with a hub, there would be a collision and they'd have to retransmit. But now that everybody uses switches, that hardly ever happens. So the early bus-based networks ran really slowly at 10 megabits per second. Then we had 10 megabits, 100 megabits, and 1,000 megabit Ethernet. And most people are now on 100 megabit or gigabit Ethernet running through twisted pair cable. This is the system used in the days of hubs, and now even now on wireless networks, if two devices, well, something similar is used on wireless networks, but you can sense multiple access. If two devices tried to transmit at the same time, the voltages would add and hit a forbidden range of voltage, so the NIC could detect that I'm getting a garbled package that is the mixture of two packets, and then it would send out a jamming signal and cause both devices to retransmit a random time later, so that they would retransmit that packet and fix it. So that's collisions on a Ethernet network. All right. And so that's what happens when there's a collision. This is really only a problem if you're using hubs. Switches prevent these by carefully directing the packets to where they're going, so that they almost never have collisions. Wireless networks use this CSMA-CA because a wireless signal falls with distance rapidly, so you cannot tell if there's been a collision because there is no forbidden range of voltage. So instead, what you have to do is before you send, you have to send a signal saying, I'm about to talk, everybody shut up. And then when everybody shuts up, then you talk. Then you say, okay, I'm done. And the next person says, I'm about to talk, everybody shut up. That's how CSMA-CA works. So it's very inefficient. You waste about half of the bandwidth arguing about who's going to talk next, but that's how wireless networks work, because they cannot withstand collisions. They have to avoid them. All right, ArcNet and Token Ring were early local area networks. ArcNet ran at 2.5 megs. Token Ring went up to 16 megs. They both used 2 rings of fiber. At least Token Ring did. Anyway, and they used a token, so they didn't have these collisions. You would have a token, you would wait for your turn to talk, and you wouldn't talk until it was your turn, and it was nobody else's turn, so there was no question who would talk. Switches don't take your signal and send it to everybody. If you send a signal, they intelligently send it just to the device you're talking to, so other people can talk and your traffic never collides, because each wire is just carrying the traffic intended just for you. The reason there are collisions on hub networks is because every signal is sent to everybody that's connected. So if two people talk at once, both of those signals will be sent to everybody. In a switch, you could only have a collision if two people try to talk to the same device at the same time, and that's not common. So it greatly decreases the issue of collisions. I don't think it's totally zero, but it's much smaller. The switch segmentation, how secure is it? Oh, it's not very secure at all. It's very easy to trick a switch into sending data to the wrong place. There's quite a few techniques. It just works under normal conditions. It's not really a security feature, it's just a traffic routing feature. For example, you can just lie about your MAC address and switches will remember the wrong MAC address and redirect it. You can also flood the switch with MAC addresses until its cable gets full, and then it will just give up and turn into a hub. To tap in fiber optics, you could cut the fiber, but that would be obvious. What you do is you bend the fiber in a tight little loop, and then some of the light leaks out, and then you put a detector here. That's how you tap it. And that'll just show up as a little bit more loss in the fiber, which will not stop it from working, and you can make a copy of the signal. These are very good questions. Anyway, so FIDI was another LAN protocol with 2 fiber rings. You had 2 fiber rings so that if one of them got cut, you could send the data the other way. The NSA room in the AT&T building, I believe, actually just terminates the fiber, adds a device in the middle. I don't think it works by bending the fiber. See, bending the fiber is how you would subtly, sneakily tap somebody's fiber without them knowing. But if you actually are authorized to go to the telco where they have end devices, you could just add more devices, which I think is what the NSA room did. You know, that's not subtle at all. That's with adding hardware to the actual network. That's like, you know, taking over your router. Like I say, hacking your router would be an easy way. But if you wanted to tap an undersea cable without getting caught, then you would have to do this thing where you bend it through a loop. Yeah, that's right. NSA ran it through special equipment. Yeah, special locked room. I mean, if you really are authorized to get into the internet service provider, then you don't need to do anything subtle. You can just add more cables, add more hardware, terminate the connection, reconnect it through another wire, you know. That's the trick. Anyway, so this is fault tolerant because if you cut the cable, the traffic can go the other way around it, not just switch port. No, you don't usually use switch. Well, you could do it with switch port, but they probably just did it by adding more devices to the network. Anyway, then you got physical network topologies on your LAN. The bus was the earliest one where you would just have a line going down here, and now if you cut it here, both of these guys lose service. So this is the really old one, like the earliest versions of Ethernet. You could have trees of them branching like this, but those are pretty much old. Then you had token ring, was like this. The actual physical wiring was a star, which we'll see, but it was logically a ring where traffic went around from this one node to the next. And a star is what Ethernet has. You have a central device, a hub or a switch, and each computer has its own cable, and it's the only one. So if one of these cables is cut, it only affects one device. Yeah, there's a photo of one of the special rooms. Yeah, you got it there. Yeah. So they added, a real rack of extra hardware to do that NSA tap. And then you got a mesh. This is what the internet does. You have multiple routes to get from one device to another. So if one of these wires is cut, the traffic can just go another way. So it's very hard to bring this kind of network down. It's more expensive, of course. You have more NICs and more wires, and more complicated to choose the path, but it's very hard to bring it down. All right, so let's try some of these cahoots. 4E, we're done with 4D, and here is 4E. Yeah, on Ethernet networks, it's a star. On the internet, it's a partial mesh. And inside your company, it might be sort of those trees where you have one network connecting to another, going to another. We kind of mixed them all. But on a simple local area network, everything is a star these days because you have one switch and everybody connected to that switch. These are good questions. Just like the OSI layers, those network topologies are oversimplifications, and in the real world, you use something that's between them or mixes them. All right, guess we can go. All right, what problem happens if you put cables near fluorescent lights? That's it, electromagnetic interference. All right, what's the most common type of Ethernet cable? That's it, unshielded twisted pair, the cheapest and usually good enough. All right, what LAN used 2 fiber rings? FIDI, yep. All right, and what physical topology is used by Ethernet LANs? That's a star, one switch in the middle, and each device has its own cable. Okay, that's 2 wins for Louis. Roman, okay. And VoIP. I think I have seen before who VoIP is. All right.